Guys, now we're starting a new chapter, right? Hello guys, now we're starting a new chapter, and we say this chapter is going to be model selection and regularization. Regularization like this. Regularization. It's going to be regularization like that, right? And we're going to use linear models as the main example because they're easier to use when we're talking about like the explanations and stuff like that, right? This video is just going to be introduction to what we'll be discussing, and then we'll get deeper into the theory in videos to come. So what we usually know is for let's say for a linear model, we use least squares to fit this model, right? b2x2 plus all the way up to bpxp. We use linear model to figure these out, to figure these coefficients out, right? I can put an error term here. I can put an error term. So when we're using least squares, there are some situations where least squares will not work perfectly. It will not give us the best results, right? So we might want a different fitting procedure because this is a fitting procedure. It's called a fitting procedure because that's the one that we use to fit a linear model. So there are times where we might want to use alternative fitting procedures. Why? Because reason number one is maybe the alternative fitting procedures result in higher prediction accuracies. So reason number one might be we use an alternative because of prediction accuracy. So the alternative ones, we are going to discuss them later, the alternative fitting procedures. But for now, the reason why we're not using least squares and using one of those alternative ones is because reason number one, for prediction accuracy. What we mean is least squares, it works when the relationship is approximately linear between y and the predictors x, and the x is here, right? This one is linear, the relationship is linear, so least squares will work very well. But if the relationship is not linear, least squares will have high bias and it will lead to very low prediction accuracy. So here, least squares is affected by the relationship, shape of the relationship between your y and your x. So which basically means the shape of my f. If my f is linear, then least squares performs well. But if my f is non-linear, least squares will perform badly. Will usually perform badly. So the relationship is very important. Also, another thing, if the number of observations that I have are much greater than the number of predictors that we have. So let's say we are looking at the credit data. We have the person's credit balance, the person's age, the person's income. Those are three predictors, right? And we have a million people, which means our n is 1,000,000 and our p is 3. So our million is much greater than p in that situation. In that situation, least squares will have low variance. So least squares will have low variance. Right? We have low variance. So it will perform. Will perform well on test observations or unseen data. Cool, right? But if my n is approximately equal to my p, let's say we have 10 observations and you have 10 predictors, right? Then variability increases. The variability increases in the least squares estimates. So in our least squares estimates, the betas and stuff like that, the variability increases. Therefore, there's poor prediction. There will be a poor prediction on unseen data. And then if my n is smaller than my p, right? Let's say we have 10 observations, but we have 20 predictors. We have 20 predictors. Then here we can no longer fit a unique least squares solution. I think we remember this from previous videos in regression, that when you have a situation where you have less observations than your predictor, you can no longer fit a unique least squares solution. So you now have infinite least squares solutions, and that will be bad, because now we cannot use it to predict anything. We don't have a unique one, right? So here the variance, what we can do now, if this is the situation, this is the situation, what we can do is we can lower the variance. We can lower variance by constraining or shrinking. We can lower the variance by constraining or shrinking the estimated coefficients. The estimated coefficients. And when you lower the variance like that, because of the bias variance trade-off, there's going to be an increase in bias, but usually the bias will be, if we shrink it nicely, the bias will increase by just a negligible amount, right? Then accuracy can increase, in which we can then use it to do our predictions. We're going to see all these shrinking methods. That is the core of our chapter. When you're doing the shrinking methods and stuff, here we're just introducing why sometimes we need to use alternative fitting procedures. Reason number one, prediction accuracy, and reason number two is model interpretability. Interpretability, or how we can easily interpret the model, right? Since it's a linear model, sometimes we might want to interpret the model. We might want to know the meaning of the value of beta naught, beta 1. I think if you remember regression, if you don't, go back to the chapters on, I think it was statistical learning, the first chapter where we're talking about modeling for prediction and modeling for you to interpret what the model is saying. So here other fitting procedures will help us interpret the model better than least squares. How do they do that? It's because some variables in the model are not exactly associated with the response. So we might have y is equal to beta naught plus beta 1x plus beta 2x2 plus all the way up to beta pxp. We can add an error term if you want, but some of these responses here, these predictors, they might not be related to my y. So in our data set, we might have all these columns. Let's just say it's an Excel sheet. We might have all these columns, right? But not every column is going to be associated with our y, whatever y we have there. So we might want to take out the noise variables, right? Because having those irrelevant variables, it can lead to unnecessary model complexity, right? Imagine our model here. Imagine our x's, they go up to x 100, right? So which means here we have y beta naught, beta 1, beta 2, beta 3, all the way up to beta 100. Right? This becomes a very complex model. So sometimes some of those variables, we might take them out because they are not related to my y. They're not related to my y. Removing them, we can remove them by setting their coefficients or their betas to 0. We can set their coefficients to 0. And that helps us to get a model that is easier to interpret. Because imagine now, instead of those 100, all of them, including them in our least squares, or let's say in our model, not least squares, because we're looking at alternative methods that allow us to remove those betas that are unnecessary, right? When you remove those, imagine now we're left with only two. It becomes easier to interpret that model and discuss what is going on, right? And this process here is called feature selection. It's called feature selection or variable selection, because we're choosing the right variables that we want in our model or that are relevant in our model, right? So the other methods that we are going to discuss, they can help us do this. But we keep saying the other alternative methods. What are those methods? One may ask, what are those methods? Let's look at the methods that we'll be discussing in this chapter. The first one is called subset selection. So subset selection, it basically involves identifying a subset of the predictors, subset of P predictors, right? We have all the predictors. Let's say here we had P equal to 100 predictors. Here we're going to identify a subset, let's say made up of a special subset made up of 20 predictors, right? That we believe are related to the response. So instead of including all the 100, we're going to just select the ones that we believe are related to the response. So the 20 that we believe are related there. Then we fit the model on these 20 using least squares. Instead of applying least squares to this 100 to everything, we first do subset selection and then we apply least squares to the ones that we think are very related to our Y, right? The second method is shrinkage. It's called shrinkage or regularization. Regularization. I think that is a spelling, if I'm not mistaken. English is not my first language, so if I'm spelling this wrong, please forgive me. So regularization, right, or shrinkage. So this basically means we fit model. In this case, we fit model with all P predictors, all of them. If there are 100, we fit the model with all 100 predictors. That's what we do, right? And then after we fit them, we shrink them. We then shrink coefficients. The coefficients that come out of those betas. We shrink the coefficients towards 0. We fit the coefficients towards 0, right? This allows us to reduce variance. This reduces variance. It reduces the variance. Cool. It reduces variance, right? And it reduces the variance, making our predictions or the performance of our model. It will increase. The performance will become better by reducing the variance, right? And also, when we are shrinking towards 0, some coefficients are actually going to go down to 0 itself. And when they go down to 0, they fall out of our model. They fall out of our model. The variables associated with those coefficients, they fall out of our model. And by that, would have done a variable selection. So shrinkage also does variable selection or predictor selection. Because if it becomes 0, let's say it's beta, the beta 90 is equal to 0. It means we no longer have beta 90, x90. So which means the x90, the variable has fallen off. We don't have it in our model anymore. So we've done variable selection using shrinkage. The third one is going to be dimension reduction. That is the third one, dimension reduction. Basically what we're saying here is, when you talk about dimension, the dimension we're talking about here is how many predictors we have. In our example, we have 100 predictors. But those may be too many to work with, right? There may be too many to work with. So we want to reduce the dimension. Not by just taking out predictors, but by taking all predictors and then we do something called projecting. We project the P predictors into an m-dimensional space. Right? It's an m-dimensional space. Basically, just imagine that here we have all the points, the predictors. We have all the predictors, right? Let's say here we have 6 predictors. P is equal to 6. Basically, we are going to project. We're going to project these 6 predictors into a space, into another space that is, let's say, 4 predictors. So our m is equal to 4. And we are going to do that using, if you have done linear algebra, we're going to use linear combinations to do this. Linear combinations. We are not removing any predictor, but instead of dealing with p equal to 6 predictors, we have created special predictors in an m-dimensional space where our m is going to be less than p. So we have reduced our dimensions that we're dealing with. Each m is going to be composed of a linear combination of these. Linear combination is basically just a sum, a function, a sum of all of these original predictors. So, for example, we can say our m1, because here we're saying we have m equal to 4, right? M equal to 4. So we have m1, m2, m3 that we're dealing with m4. So our equation becomes something like y is equal to m1. Let me just for what do you call this? For ease of explanation, I'm just going to use a vector x, right? Y m1x plus m2x plus m3x plus m4x. Like that, right? So here, instead of writing y is equal to beta 1, beta 2, beta 3, beta 4, beta 5, beta 6, beta whatever, up to beta 100, we are not just writing it like this, where each m1, each m, so m1 is going to be a linear combination of these. So it might be 2 times x1 plus 3 times x2 plus 10 times x5 plus 6 times x 6 or whatever it is. And then here we have another equation that represents m2, m3. M2 is going to be maybe 10x1 plus 20x2 plus 15x5 plus 6x6. And then m2 will be another equation. So these are the linear combinations. They're basically just the addition of the original predictors that we had. And then now we are dealing with a special dimension. We have reduced the dimensions from 6 to 4, and we deal it with a new equation. We deal it with a new equation here because it might be easier for us to fit the model using using those reduced dimensions. We're going to see the videos when we do dimensional dimension reduction. But these are the three methods that we are going to be or alternative fitting methods that we're going to use: subset selection, shrinkage or regularization, and dimension reduction. So here we are going to emphasize using a linear model because it's easier to explain. But these methods can also be applied to a classification setting. They can also be applied to classification. So in the next video, we are going to start on subset selection. So stay tuned for that video.